Well, good morning, everybody. Let's go ahead and get into Chapter 8 in the OTCO workbook, which is activated sludge. Um, the schedule in the OTCO workbook calls for spending a week on activated sludge. Honestly, I think this chapter and also the chapter on sludge digestion probably could benefit from spending a couple of weeks on it. There's a lot of material to cover. Um, I did create a YouTube channel, Chapter 8, where I've linked to a video about activated sludge from the Pennsylvania Department of Environmental Quality, or whatever their version of EPA is. Video is a little dated, but it does a pretty good job of covering the basics of activated sludge. So for my part of the presentation, I wanted to really cover process control and the mathematical formulas that you're going to see in your homework, and how they actually can be used practically in controlling processes at an activated sludge plant. So with that being said, let's go ahead and get started. So in controlling the activated sludge process, what are we really trying to accomplish? Activated sludge, like the trickling filters and RBCs that we covered a couple of weeks ago, use bacteria that occur naturally in wastewater. So really what we're trying to do is create an ideal environment for those bacteria, and more specifically for the type of bacteria that we want uh, to dominate the growth process. Bacteria, of course, grow uh, exponentially, and certain bacteria will thrive in certain conditions. So what we're trying to do is create the conditions so that the right type of bacteria, which for our purposes are going to be bacteria that are going to clump together and flocculate and settle well in a final clarifier. Those are the type of bacteria that we really want to select for. And because bacteria grow so quickly and multiply, if we can create the right environment, then the desirable bacteria are going to outcompete undesirable bacteria and give us uh, the type of growth that we want. On the other hand, if we create an environment that is more favorable for undesirable bacteria, say bacteria that create too many filaments, or that cause sludge bulking, or a variety of other problems in the process. If conditions favor those bacteria, they're going to outcompete the bacteria that we want to grow. So our main goal with process control is to create an environment where we get the right type of bacteria. And we do that by providing enough dissolved oxygen. Typically in domestic wastewater, we do not have a problem with nutrient deficiency. If you're working at an industrial plant, or ever work at an industrial plant, you may have to add nutrients to get the right type of bacteria growth. But in domestic wastewater, usually we don't have a problem with that. And then, of course, we want to provide adequate dissolved oxygen. And what you're going to see in the course material is for conventional activated sludge, we want to have at least one, preferably 2 milligrams per liter, to provide enough oxygen for the right type of bacteria to grow and thrive. So in the OTCO coursework, there are basically 3 different formulas that show up in your homework, and I'm going to cover 2 specifically that I think are really important for you to understand and be able to apply. And then the third formula I'm going to basically tell you to ignore. because you're probably not really going to see it on an exam or anywhere that you work professionally. So the two that I definitely want to cover are mean cell residence time, or MCRT. Uh, Now this also is known as solids retention time, and somewhat confusingly, in our industry, a lot of people refer to it as sludge age. And I don't want you to confuse that with the sludge age formula in the text. And that's something in the textbook that I really wish they would eliminate in the ODCO part of the coursework, because that term is usually used interchangeably with MCRT or solids retention time, and it can be a little bit confusing. But mean cell residence time or solids retention time is kind of a theoretical number of days that a microorganism would exist in the activated sludge process before it's wasted out of the treatment process. So this is a theoretical number. It's expressed in days, usually to, say, 1 decimal point. And it is derived by taking the pounds of activated sludge available for treatment. So the mixed liquor suspended solids in the aeration tanks, as well as in the final clarifiers, and dividing that number by the pounds of solids that are removed daily from the process. So this would be pounds of suspended solids removed through wasting activated sludge, as well as the pounds of suspended solids removed from the system in your final effluent. So basically, pounds available for treatment divided by pounds removed is going to give you a number that we refer to as days, theoretical days, for your mean cell residence time. The other formula and other calculation that we're going to focus on is the food to microorganism ratio, or FM ratio, and that is derived by calculating the pounds of biochemical oxygen demand, or BOD. That would be your food. Pounds, so think of it as pounds of food divided by the pounds of microorganisms, and we get pounds of the microorganisms by calculating the mixed liquor volatile suspended solids. So pounds of mixed liquor volatile suspended solids represents the pounds of microorganisms. So this is a ratio, as you'll see in the textbook and also on the video. For a conventional activated sludge plant, we typically want that FM ratio to be between 0.2 and 0.5. And we'll go ahead and get into each of these formulas in a little bit more detail here. So a couple things about this MCRT formula. There are different variations of it. The basic formula is the same. The only question is, do you include the volume of the final clarifiers when you're calculating the pounds available for treatment? And secondly, do you account for the pounds of suspended solids in the final effluent when you're calculating the pounds being removed from the system? So it can be done either way. The most important thing for actually using this formula for process control is that you pick one and do it consistently. For the purposes of the class and for most of the questions that I've seen on exams, they're going to ask you to use the volume of the final clarifiers. That should be expressed in the way the question is worded. So typically on an exam question, you will use the volume of the final clarifiers and add that to the volume of the aeration tanks to calculate the pounds of mixed liquor suspended solids available for treatment. And then you will have to account for the pounds of suspended solids leaving the plant with the final effluent. So Typically, when you're calculating pounds available for treatment, the formula is going to be the volume of your aeration tanks plus the volume of the final clarifiers times mixed liquor suspended solids in milligrams per liter times 8.34. That's going to give you a number in pounds that goes above the line. And then below the line, our pounds wasted is usually going to be calculated by multiplying the gallons wasted per day in million gallons. So remember, you have to convert, let's say if you had 150,000 gallons, you have to convert that to million gallons to plug into the pounds formula. So it would actually be like 0.150 million gallons. So gallons wasted per day times, usually it's going to be return activated sludge suspended solids. That's the only way that I've seen it calculated on an exam. They're just assuming that the plant is going to waste from the return activated sludge line. So it's going to be gallons wasted times return activated sludge suspended solids times 8.34. That'll give you your pounds wasted. And then pounds leaving in the final effluent is going to be your plant flow in million gallons per day times the final effluent suspended solids, which is usually a pretty small number, times 8.34. So add pounds wasted and pounds in the final effluent together, and that's the number that's going to go below the line. Some plants in real life do actually waste from the aeration tanks, but I've never seen that expressed that way on an exam question. So also generally with mean cell residence time, typically at a conventional activated sludge plant, we look to have shorter mean cell residence times in the summer because the microorganisms are much more active and grow quickly. And then in the winter time, because their growth is slowed and as well as their general activity, we're going to hold longer MCRTs in the wintertime. So that's a basic fundamental concept of operating an activated sludge plant. Shorter MCRT during warm weather, longer MCRT in the winter when the bacteria is less active. So what do we actually use MCRT for? These types of questions you're not going to see in your homework, and you're probably not going to see on a class 1 wastewater exam. But I wanted to give you a little bit of information on how to practically use this in operating a plant. And the way that we would use this here is that we would pick a target MCRT. So let's say that we wanted an MCRT of around 10 days. What we would do is calculate the pounds of MLSS that we have in the plant and divide that number by our desired MCRT. So in our case, we'll say divide it by 10. So let's say we had 30,000 pounds of MLSS in the plant. We divide that by 10, and that would give us 3,000 pounds, and that would give us a total amount of pounds that we wanted to waste from the system. At that point, we would take that 3,000 pounds and we would plug it into our pounds formula and try to figure out how many gallons we need to wind up wasting. So in this case, we would take our 3,000 pounds, divide it by 8.34, divide again by the return activated sludge suspended solids, and then we're going to wind up with a number of gallons to waste. So let's carry this through a little bit. Let's say that we knew that we wanted to waste our 3,000 pounds out of the system. We divide 3,000 pounds by 8.34. And then let's say that we knew that our return activated sludge suspended solids was around 5,000 milligrams per liter. So we divide again by 5,000, and that is going to give me in my calculations, 0.072, which means that I need to waste 72,000 gallons of return activated sludge out of the system. So let's say that we're already wasting 100,000 gallons a day out of the system to maintain um, our mixed liquor suspended solids where it is currently. So if we needed to waste an additional 72,000 gallons, we don't want to do that all at once. We want to do that over a period of, let's say at least a week. Uh, Microorganisms do not react well to sudden changes, so we want to do this slowly. So if we knew that we needed to waste an additional 72,000 gallons out of the system, and let's say we wanted to do that over 7 days, we might increase our wasting rate by 10,000 gallons a day, and hopefully at the end of the week, we would be close to our desired MCRT. So that's a practical way that we use this formula for everyday operation at our plant. Picking a target MCRT and then calculating the amount of gallons uh, that we would have to waste out of the system, and coming up with an adjustment to our wasting rate to get to where we want to be. Okay, so let's talk about the second formula, which is FM ratio, food to microorganism ratio. As far as practical application, this is something that we would use kind of in conjunction with MCRT to develop a strategy for operating our plant. And the reason that we do that is it's really difficult to run a plant off a constant FM ratio, just because, number one, we are operating uh, as far as calculating the FM ratio on the BOD test, which, uh, as you'll remember, you get results 5 days after you initiate the test. So if I tried to operate this plant on FM ratio, I would be using information from a sample that's 5 days old. And as we just discussed, with adjusting for our MCRT and that taking, uh, you know, oftentimes up to a week to get to where we want to be, I would be using 5 day old information to try to pick a target of where I wanted to be 7 days from now. There's almost like a 2 week gap between the data that I use and the end result. And by that time, conditions may have changed. So usually what you want to do, or what I would advise doing, is uh, finding out what your typical, say, average primary effluent BOD numbers are for different times of the year. Now here in Perrysburg, the flow doesn't change much. We're not like Bowling Green, where the population changes with the school year, or maybe uh, a town with a canning factory or something like that that has different production runs. Our influent is pretty consistent. The only difference being when it rains. So I can go back and look at historical data over the past 15 or 20 years and have a pretty good idea, based on the time of year and the average daily flow, of what my primary effluent BOD is going to be. So I can calculate the F part of this uh, equation pretty easily. And then as far as the microorganism part, if I know that I want to try to get somewhere between that 0.2 and 0.5 FM ratio, I can divide my pounds of primary effluent BOD by, say, 0.2, and that is going to give me a number in pounds of mixed liquor volatile suspended solids that I want to maintain under aeration for treatment. So just as an example here at our plant, with all 3 aeration tanks in service, My aeration tank volume is close to 2 million gallons. I know from past experience and from the history of the plant that our mixed liquor suspended solids is usually 70% volatile. So if I calculate the amount of pounds in the aeration tanks at different concentrations of mixed liquor suspended solids, I can find uh, a number that is going to give me an FM ratio close to 0.2 uh, that I want to keep the plant at. So we use this in conjunction with MCRT to give us an idea of how many pounds we want to keep in the aeration tanks, and then I can plug that into my pounds formula to give me an ideal mixed liquor suspended solids concentration. And then as far as operating our plant, once we know what our mixed liquor suspended solids concentration, what that target number is, then the way that we operate the plant here is when we approach that number, we'll lower our wasting rate a little bit as that mixed liquor suspended solids number starts to creep up. Uh, we'll increase the wasting rate. And so basically, if we're trying to keep, let's say, our mixed liquor suspended solids around 1500, we might say, let's pick a range between 1250 and 1750. When our mixed liquor suspended solids gets up to 1750, we're going to gradually increase the wasting rate until that number starts to drop. And we'll let it continue to drop until it gets down close to 1250. When we get down to 1250, maybe 1300, we'll gradually start reducing the wasting rate until that number starts to creep back up. So take a look at this slide. This is the last one in my presentation. This just gives you some real uh, actual operating data from our plant to show you how we do this. With our influent flow at 4 million gallons per day, our primary effluent BOD is typically right around 100 milligrams per liter. So we run that through the FM formula. We know we have about maybe 3,300 pounds of BOD. Because we know our aeration basin volume, like 1.9 million gallons if they're all in operation, we know that our MLSS is usually 70% volatile content. So if we had our plant running at 2,000 milligrams per liter mixed liquor suspended solids, based on that operating data, our FM ratio would be around 0.15, which is pretty low, kind of lower than the 0.2 to 0.5 that we would like to be at. So we ran the calculation again and found that if we were around 1,500 milligrams per liter in the aeration basins, then our FM ratio would be right at that 0.20. So that's how we picked our operational strategy. And the reason that we did this is my predecessor here at the plant, the guy that left when I moved up to be the plant manager, when he started here, he just told us, hey, I want the aeration tanks at 2,500 milligrams per liter. And we kind of knew from experience that that number was too high, that we were going to have too many microorganisms and not enough BOD coming into the plant, that would create operational problems for us. Again, as I mentioned, if you have too many microorganisms and not enough food, you're going to not get the right type of bacteria. We were having problems with filaments and other issues. Had a really old sludge that settled very quickly, which created some issues with what is known as pin flock, just little pieces kind of old dead sludge that carried over in our final effluent. Not enough to create a violation, but the plant was not operating as well as it could. So we were able to to go back and do the calculations and show that we would be better off running the plant closer to 1,500 milligrams per liter instead of 2,500. And again, that's just kind of an example, a real life example of how these mathematical problems that you're doing in your homework can be applied practically to run an activated sludge plant. So, all right, that's all I've got for today. I'll start putting together videos for the math problems to show you how to do them. Continue working on those midterm exams and send them back to me when you're done. I did have a couple come in. I'll let you know if on the math problems, if you do them and get them wrong, I will try to give you hints and let you try to correct what you got wrong and resubmit them, and I will give you credit for them. All right, all I got for today. All right, hopefully everybody's safe and healthy. Take care. Bye-bye.